we present DataDAM, efficient dataset distillation with attention matching, as new state-of-the-art method for creating smaller synthetic datasets. In computer vision, datasets are typically quite large, with ImageNet having 1,000 classes and SA1D ranging in 1 billion annotations over millions of images. There must be some redundancy in this data that can be exploited to make training more efficient. Traditional approaches to lower dimensionality, like principal component analysis, can reduce the size arbitrarily. However, this ignores any discriminative features and often makes outliers all but unlikely to find in the reduction. Similarly, course-set selection was introduced to help combat this problem. However, selection methods are often highly prone to overfitting, making them significantly less generalizable when test sets. But what if we chose to learn a subset of this data? Let's call the data T and our subset of synthetic images S. Could we then be more confident that our smaller data set accurately contains the information from the original data set? Well, this is the exploration of dataset distillation. Previous works have introduced several novel approaches to dataset distillation, each with their own set of limitations. Performance matching and label distillation often involve heavy computational footprints. Meanwhile, gradient matching inherently expresses a bias in the distillation process. Distribution matching circumvents conventional bi-level optimization, however, at a significant cost in performance. Finally, matching train trajectory incurs the expensive cost of training several expert models. Ultimately, this all boils down to being difficult to optimize, containing biased samples, lower performance, or computationally intensive. So overall, less efficient than the method that we're trying to produce. In our work, we aim to address these shortcomings by introducing an efficient method of dataset distillation. In particular, we use attention to extract and match the meaningful information from intermediate features. Once again, without bi-level optimization, we perform attention matching on the intermediate feature space, regularized by maximum mean discrepancy on the network output. We then backpropagate this directly onto our synthetic image, thus benefiting from not training our models. Similar to previous state-of-the-art, we benchmark our results on CFAR10 and 100, as well as tiny ImageNet and ImageNet 1K at low and medium resolutions, respectively, using the standard 1, 10, and 50 images per class, as seen in the image. We take this a step further by reporting results on high-resolution ImageNet subsets, including ImageNeat, ImageWoof, and ImageSquad. We further explore data distribution of our synthetic sets over the original dataset and show better coverage of class embeddings when using DataDAM. Our further experimental results over varying IPCs, or image per class, show robustness of our method, as well as cross-architecture and low computational footprint in the distillation process. Finally, we present our performance on 2 applications: continual learning, which shows superior performance with DataDAM. Meanwhile, neural architecture search is improved in terms of correlation and performance at a smaller time cost compared to conventional methods. We thank you so much for watching and hope you'll check out our paper and poster at Nord Room number 100 in Paris. We hope to see you there.